Right, so now let's have a look at this geometric interpretation of duality in the context of linear programs. So let's take this x bar being an optimal solution for our primal problem, and then now I'm posing my problem in a way that I'm showing the the constraints for each row of the matrix A individually. So one interesting way of thinking about what duality actually means, it's associated with this notion of having a particle, like an object, that is being pulled towards the direction minus C, like because we're minimizing in opposite direction of the vector C, so it works like we're pulling it within this polyhedral set formed by these constraints. And once we pull it to a point, it gets stuck within the polyhedral set. So to put that in a picture, it would look like so. Here. So basically, pretend that there is a string. So this is the vector C in this direction. So suppose that there is a string pulling into the minus C direction here, and I'm pulling this downwards. And my feasible region is composed by these hyperplanes. So it's this big polyhedral set there. And then when I pull in this direction, what happens is that eventually it comes and it gets stuck at exactly this point, right? So at this point here, what you have is this equilibrium caused by the reaction caused by this wall and the reaction from this wall by the action of pulling this into this direction. So it's precisely this equilibrium. It is formed by looking at these vectors a1 and a2, and they end up being scaled accordingly by these multipliers p, such that these two vectors are in equilibrium with the vector minus c. So another way of saying it is saying that it's almost like writing C as this combination of A's using P. It is not a linear combination because it has this additional condition. We'll talk about more cones in the next class, but this is what we define as a conic combination. It's a linear combination plus the condition that your reals have to be non-negative. So this kind of, it is the same as saying that you want your vector C to be within the cone formed by these two elements. Or if you prefer, you're pulling this in this direction and you're finding this equilibrium. There is an interesting thing in that is associated with this vector, because this vector is not part of the equilibrium at all. What we're doing with it is that for the P multiplier for this is 0, because that vector is not exerting, is not being part of this equilibrium. So that's another way of thinking of, so dual optimality is associated with finding these P's such that the equilibrium associated with the active constraints or the walls touching the point is correctly set. So this actually leads us then to this sort of interesting notion of complementary slackness. Complementary slackness is basically telling us the following: this relationship is always true because of two things. Either my constraint is active, so A is the vector A is part of that equilibrium that is being formed, and because so, this term takes a value. But because B equals A transpose X, this is true. Now, for all the other constraints that are not active and being such that this term differs from this, then in order to guarantee this, to guarantee that equilibrium, the value of the coefficient P becomes 0. So complementary slackness means that you either have a slack and then P is 0, or if you have no slack, then B can take a value different than 0. So with that idea in mind, you know, if you will look again at how we define a PB, I find it easier actually to read from right to left to this. So we start from now where optimal solution X. We know, we just seen that we are writing the vector C as a combination of the vector A, of the vectors A with the with my vector P's, and only those that are actually touching X would be different than 0, while the others would be 0. And then if you look at the vector C and look at that, and then you post multiply by X, so you get this. And you know that this is going to be, you can replace this with B, because for those that is not true, the P is going to be 0. And then that takes us exactly to the value. So it's kind of another way to demonstrate how strong duality goes. And because this is only holding because of that, then you can see here that this is also can be seen as optimality, an optimality condition. Because once you show this, we can use the item 3 of the corollary 2 you saw in the previous video to attest optimality of P. So that leads us to this theorem 4 called complementary slackness. So what complementary slackness says is that if you have X that is feasible for the primal and you have a P that is feasible to the dual, they written like such, you can say that F, X, and P, they are optimal for their respective problems if and only if your complementarity conditions hold for the primal and complementarity conditions hold for the dual. And that is sort of a derivation of the other two results. Here is a proof, and basically the proof is based on what we've seen before in terms of weak duality, strong duality, and that corollary to item 3. So we even used this before, and we used the notion that these elements, they match in sign to prove strong duality. So that's exactly what we had as before. Okay. Some remarks. So in the non-degenerate case, complementarity slackness determine a unique solution. Because if you look at this system, for example, this yields this one here. And that of course only holds for these basic variables at the optimal. And because we know that the rows are assumed to be the columns are assumed to be Li, the solution for this, when I look at these only the basic variables, it's unique. So so if this holds and we're talking about non-degeneracy, it pretty much means that your P's are unique as well. Your dual variables are also unique. And of course, this is not the case for the degenerate case. Even truly, you can't use complementarity conditions to obtain dual solutions. It's basically, it really doesn't work because you might have zero values for P's for active constraints, and that's where everything gets a bit more complicated. So in the degenerate case, you can't simply rely on complementarity slackness to decide on optimality of your dual variables. All right. So here it is. This all leads us, and this notion of looking at geometry of dual feasibility kind of leads us into this. Is the last part we needed to define what we call the optimality conditions for linear programs. There is another way of arriving into these. If you ever heard of something called Karush-Tucker optimality conditions, this is kind of exactly how they look like for linear programs as well. But because we're not talking about KKT optimality conditions, this is for nonlinear optimization. Well, we got here through a different avenue, but here we are. So this is what we call a primal dual pair, basically a primal solution and its respective dual solution. We've seen in the next video that we can see the relationship between these two by looking at, for a given basis B for X, you can look at P as being CB B minus 1. So for a given basis, and you can calculate your X, we know, by B minus 1B. So this is the connecting term between the two. So that's how you form a primal dual pair. And these are the conditions that we have to observe to find that these are optimal. Primal feasibility, you have to have a primal solution that is feasible. Dual feasibility, which is represented by this constraint here, and plus the non-negativity of the dual variables given canonical forms like we've been seeing. And the last one is for those constraints that are not active. So this set I 0 is the first time we're looking into that. Is the set for which the slacks are 0. You can think about that. You can think it like that. So for all constraints, this is equality. So for those that are not in I0, this has to be set to 0, and that's the last condition that was missing. We saw primal feasibility, and we saw dual feasibility, and we just having this third one, which is complementarity slackness. Oh, complementarity conditions, as we sometimes call it. One interesting thing is that if you look at these two conditions simultaneously, is that you can see that this is holding just like because of the picture we saw before. I mean, C can be expressed as a non-negative linear combination of your vectors A of the active constraints. Okay, because this is the case for all constraints, and you know that these are 0 for the non-active constraints coming from this. When you combine this two plus this one here, what you get is this, which is that geometrical interpretation that we started with. So basically saying that only active constraints have a role in defining optimal solution. I have a picture here kind of showing how this looks in terms of dual optimality and dual feasibility. And I also bring in the case of what happens when you have degeneracy. Okay, so it's kind of an involved picture, but let's look at it little by little. So one interesting thing I should probably mention is, notice that optimality is the combination of primal feasibility and dual feasibility, you see, and of course complementarity conditions. But because complementarity conditions are supposed to hold for basic feasible solutions, you're trying to find when you're doing, say, primal simplex, is that you start with a primal feasible solution, you go searching for something that is also dual feasible, because primal feasibility plus dual feasibility, given that you're talking about basic feasible solutions, you will have, solutions that satisfy optimality conditions. We'll see a bit more of that in the next video, but I wanted to make that remark here. So here is the picture I was on about. So let's look at this slowly. So basically what I have is a polyhedral set formed by these constraints here, and I have an extra redundant constraint here too, because I wanted to cause some degeneracy. And what I'm showing you is the problem in which I am trying to optimize in regards to C. So I want to minimize, meaning that I want to go in the direction minus C. So the direction minus C takes me to this optimal point here. Okay. And there is something interesting in terms of observing that it is optimal. Notice that, like we just said, optimality, primal optimality means dual feasibility. And we just seen that dual feasibility is the same as having your vector C being written as a conic combination, or a combination of the active constraints at that point. So let's look, for example, at point A. So point A is a point that is neither primal feasible nor dual feasible. It's not primal feasible because it's not within the polyhedral set that defines the feasible region. And it is also not dual feasible because I cannot write C as a combination of these vectors. I don't know if you can see, but C has a tiny little component, an inclined component here, meaning that these two things, I wouldn't be able to write that. So it's not in the cone formed by these two vectors. Remember that I can only use remember that I can only use positive p's, so I would need a component going in this direction to fix it. Now B is primal feasible, but once again I cannot write with only positive combinations of A, so making A this big and B A2 this big, write C, because I'll have to flip one of them to get the right component. So it's primal feasible, but it's not dual feasible. Now look at C. C is primal feasible because it's within the polyhedral set, and is also dual feasible because I can definitely write C as a combination of this vector and this vector, a conic combination of them. So it's within the cone formed by the vector C. So that classifies primal feasibility and dual feasibility, and I can hold complementarity conditions hold in a sense that I can make A5, A2, A6 for what it's worth, and A4 have p-value 0. Now look at D. D is an interesting character because I have 1, 2, 3 constraints, so I have 1, 2, 3 vectors, and therefore it's degenerate. So if you ask me whether D is dual feasible or not, the answer for that is depends. It depends what basis you are considering. Because if you consider a basis for this vertex where you're using A5 and A6, then C is not dual feasible, therefore wouldn't satisfy optimality conditions. But if it happened that you actually looking at A6 and A1, then it's actually dual feasible because it's within the cone forming the two vectors. It's not primal feasible, right? But that could be the reason why I was searching, I put it here is just because I needed more space to draw things. But it could have been that this point is degenerate with another constraint here. So it could be primal feasible and degenerate, okay? So you can see what happens here. As soon as you have degeneracy, you can simply rely on your complementarity conditions because it might be just killing this vector. And if it's killing this vector, then this thing is not feasible. So you kind of have to make sure you're removing the correct vectors, either this or this, to make the basis, to make a dual feasible basis for this problem. So that's the issue with degeneracy. It's similar to the case in the primal that we were looking at. When we pick the bases, we might be picking bases that might by being feasible. So there it is. And you can see here that once you have primal feasibility and dual feasibility, you got everything you need. You get complementarity conditions by construction, and you have everything you need to attest that C is optimal. Okay? All right, so we'll stop here with this video, and in the last video coming next, we'll talk about some applications of duality. One very practical that we're going to use already, and then we'll talk about the dual simplex method. So see you in the next video.